Now, infinitely large sheets of current and infinitely long wires, these things are only academic. They do not exist in real life. However, I can take a very long wire. I'm going to bend it into loops like this, tightly wound together. I will get a device that I can use in the real life, and it's called a solenoid. A solenoid is very useful because I can then generate drive a current through the solenoid, and then that solenoid will produce a magnetic field which behaves similar to the natural magnetic field of a magnetic bar. Okay, see how that works. First of all, suppose I have a current flowing in a solenoid. Basically, it's just you take a long wire, you turn into circuit loops and compact these loops very close together. Okay, what is the general direction of the magnetic field lines? Well, you can add the direction of the field produced by each circular loops using the right-hand rule, so it points this way. Okay, so it points this way, and it has to curve around and come back, right? So imagine here the solenoid. I'm going to make it smaller. Okay, I'm going to make it smaller, and then you can think of magnetic field lines like this. So the field lines will emerge from this end of the solenoid and would just disappear into the other end. Isn't that kind of similar to the case of a bar magnet with a north pole here and south pole there? Okay. Now, of course, this is an electromagnet because it's not a natural magnetic stone. It only produces a magnetic field when I drive an electrical current through it. When you turn off the current, there is no magnetic field, so we call it electromagnet. Okay. What I want to know is, if you have a very long solenoid, you look at a point that's far away from either end. Okay, at that point in the interior of the solenoid, can you tell me what is the value of the magnetic field? Okay, what is the value of the magnetic field? Now, I'm going to redraw this picture a little bit. I'm going to concentrate only on the top and the bottom edge. Okay, I'm not going to draw those. What I'm going to do is imagine what happens on the surface, on the top of the solenoid. You can see here I've got a whole bunch of current going in, so you get a whole bunch of currents going in, right? Uniformly distributed. And you look at that edge, I got a current coming out, so it's like that, right? And that extends to infinity this way and extends to infinity that way. And you can see that gives us symmetry. If you wind these wires uniformly, each segment carrying the same current I, then as you look at an infinite long straight solenoid, you look at this point here, then by symmetry, the magnetic field should point this way along the axis of the solenoid, and it should have the same magnitude anywhere, right? Because no matter where you're looking at, this point, you are far away from either end, so you just get the same result. So you get a magnetic field line distribution like this. So if I want to use Ampere's law, I have to choose a loop, and one segment of that loop obviously should include a straight line like this to capture the symmetry. Okay. Now I have to self-enclose that loop. So how should I continue? Well, you got field lines that are parallel to the orientation of the solenoid. So if I get out vertically like that, from here to there, I'm not going to pick up any contribution to the Amperian integral. Now I have to come back. So what do I do? Well, let's say I'm going to come back like this. Okay, I'm going to come back like this. So I'm going to basically draw another rectangular loop. You know what happens here? It's easy to calculate. You know what happens here and there. That's basically 0. The only thing left is how do you calculate the contribution of B dot ds from here to there? Okay, from here to there. Now remember, this is the exterior. Okay, exterior. Here's the thing: if you have a very long solenoid, okay, the way I draw it, this is not a very long solenoid. But if you did have a very long solenoid, imagine what happens. You have all these magnetic field lines. Each of them has to form a loop. They cannot break somewhere in the middle. They have to form a loop. Suppose, just for the sake of argument, you say you got 10,000 such lines. Okay, 10,000 such magnetic field lines inside. then outside you must also have 10,000 such lines, right? Because the field lines must form one loop, part of it inside, part of it outside. What's the difference though? The difference is that when you're inside, all these 10,000 lines are packed together within a narrow interior. You got 10,000 lines, so the field is very strong, right? On the other hand, outside, except at the two poles, the field lines are further spread out. The same 10,000 lines occupy much bigger space. Okay, so if you pick up a point here, you say outside, you say, what is the field strength here? Well, the field lines have to occupy an infinitely large space outside for the same number of field lines. So therefore, the density of the field lines is much lower. And if this thing is infinitely long, you can imagine the density of field lines outside would be pretty much zero. Okay, and therefore, what do you think should be the magnetic field here or here? Pretty much zero. Okay, unless the solenoid is not infinite long. That would be another matter. So I'm going to say the B field is 0 here, no contribution here, no contribution here. The only contribution to the loop integral comes from the red segment. Let's say the length of the red segment is L. Okay, let us integrate B dot ds. What is that equal to for this contour? You only have to consider this segment, the red segment. For the red segment, you have B dot ds over the length L. Okay, over this length L from here to there. And B and ds have the same direction, so this is just B ds. And B has the same magnitude. I'm going to take that B out. It's all the same as we did before. ds, that is just L, isn't it? Okay, so this is BL. On the other hand, what does Ampere's law tell us about the other side of the equation? It is equal to mu naught times what? All the current captured or enclosed by this loop. Alright, you don't have only a single loop penetrating, a single loop like this penetrating. There are a whole bunch of loops. How many loops? Well, that depends on how closely you pack these loops, right? Suppose the number of loops per unit length that you pack in is n. Okay, number of loops you pack per unit length of the solenoid is n. And the length of that segment from here to there is L. So what do you think n times L would be? Wouldn't that be the total number of loops of current that you pack in between here and there, right? And each of these loops, each of these circular loops contribute a current I, right? You get, like, let's say count here, 1, 2, 3, 4, for example. You get 4 loops. So each of them contribute a current I, so the total amount of current captured is n times L times I. Make sense? Okay, you cross out L, you get B equals what? Mu naught n times I. Okay, this is the expression for the magnetic field in the interior of a long straight solenoid. Look at dimension. It's mu naught times what? Current should be divided by length. What is the unit of n? The number of loops per unit length, so that is 1 over length, so that makes sense. Mu naught Ni. How do you get a large magnetic field out of a solenoid? You would need a large current, which of course makes sense. You also need to pack these currents closely, so the loops get very close to each other. That is n, the number of loops per unit length. Okay, so it makes sense. B is proportional to n and proportional to I. Alright, so that is the magnetic field inside a very long solenoid far away from either surface, from either ends. If you want, you can also figure out the magnetic flux, the magnetic field near or at one of the ends of a semi-infinite solenoid. So you suppose you have a solenoid that's like this. This end goes to infinity, but you're looking at here, so you don't have the other half. Okay, you're right here. Let's say you got a whole bunch of current flowing like this, right? So this really, if you follow the right-hand rule, this is where the field lines come out. So really, this resembles the North Pole of a bar magnet, right? What if you want to know how strong the field is here, not somewhere inside? Okay, what is the field right at the pole? Is it the same as mu naught Ni? Well, no, it is not. Okay, it turns out that if this is semi-infinite long, or at least very, very long on that side, then right at either pole, North Pole and South Pole, the B field is about half as much as the B field in the interior. Why is that? Can you figure that out? Well, I want you to think about and figure that out using this as an input, using this as a condition, something you already know, plus the idea of superposition. So you don't have to start from scratch. You can get that result instantaneously, well, at least very quickly. Okay, so that is what's called a solenoid. Now, another useful device that creates a magnetic field is called a toroid. So what I have here is I start with a long solenoid, okay, and I'm going to take that solenoid, I'm going to bend it into a circle. That is called a toroid, like this. So in this particular case, I have a circular piece of wood or whatever, and then what I'm going to do, I'm going to wind wires around it like this. Okay, so I can lead the current in, and here the current flows out. And I want to know what is the magnetic field in the interior of the toroid. In fact, if you look at the toroid from afar, it looks like what? A current loop, right? A single current loop. But what about the magnetic field here? Okay, what about the magnetic field here? How would you find that out? Well, again, see if you can observe some symmetry of the problem, and if there's enough symmetry, then you can use Ampere's law to solve the problem, right? This problem obviously has symmetry. Suppose the winding is uniform, okay? The number of turns per unit length n is uniform. Then, what is the symmetry of the problem? First of all, the magnetic field lines, look at the direction of the current. It should point what? It should form clockwise rings, right? The field line should go like this. And secondly, anywhere on the same circular loop, concentric with a toroid. Okay, concentric. So I'm drawing a loop like this. The magnetic field line should have the same direction. I'm sorry, or tangential direction, the same magnitude throughout, shouldn't they? That's the symmetry of the problem, right? Okay, so what kind of Ampere loop should I take now? Yeah, you should take a loop like this. Okay, so I'm going to take a loop like this. So on that loop, I get B dot ds as usual. What is that equal to? That's the contour. That's the contour C. BDS, first of all, BDS, because B and ds are both tangential. And then B has the same magnitude because of symmetry. So I'm going to take that B out. And what's the integral over ds? Circumference, okay? If the radius of this loop is r, then that is B times 2 pi r. Okay, what is that equal to? What is the right hand side of the Ampere's law? Mu naught times what? The total amount of current captured by this loop. Does it only capture one segment, I? How many times does these current penetrate this loop? Well, every time you have a little like this, it will penetrate once, right? Suppose there are a total of n turns. That will be n times I. Okay? N times I. So B therefore equals what? Mu naught n I over 2 pi r. That is the magnetic field in the interior of a toroid. Okay, it's kind of similar to the case of a solenoid, but not identical. It actually depends on R. The further you are out, the weaker the magnetic field, because it's generated by the same current, but it's more spread out over a bigger circle. Okay, now, in the case of spherical and cylindrical capacitors, we learned that these capacitors will behave like parallel plate capacitors under the right kind of approximation. And that is when the inner outer surface of a capacitor are very close together, so you look in a very narrow gap. Anywhere inside this very narrow gap, you look at the two surfaces, the two spheres, the two cylinders, they look very flat, right? So they look like a parallel plate capacitor. Now in this case, how is it possible? Is it ever possible for a toroid to behave like a solenoid? The difference is that the toroid is curved around, the solenoid is straight. Okay? But imagine, suppose I have a very skinny toroid, okay, like this. See, a very skinny one. Right? So this is quite thick, but I have a very skinny one, like this. So if you're here, from your perspective, both the inner and outer layer look very straight, so you can say it's almost like a straight bunch of wires. So that of course produces it resembles a solenoid, right? So imagine R does not vary by much. It can vary between here and there, right? But if it doesn't vary by much, okay, it is roughly basically equal to big R. Big R is just, you know, the distance between the center of the symmetry of the toroid and either the inner or outer surface. Makes very little difference because this is very narrow. Okay, this is very narrow, very narrow. So in this case, B then approaches what? Mu naught over 2 pi. I'm going to write Ni over big R. Okay, what is 2 pi times big R? Isn't that the circumference of the toroid? Circumference toroid. Okay, so what about this? What about N over 2 pi? What's N over 2 pi R? That is the total number of turns divided by the total length. What, isn't that N, small n, the number of turns per unit length? Then times I. Recognize that? That is the expression for the magnetic field of a solenoid. See that? Okay, so you see, under the right approximation, the toroid expression for the magnetic field is the same as that of a solenoid.